is Hanna Shin. I'm a junior at Ivy Collegiate School, and I'll be talking to you today about number theory. So we'll be going over prime numbers, composite numbers, and modular arithmetic at the end of this part one of number theory. So starting with the definition of number theory is a branch of mathematics that deals with the relationships of numbers, especially positive whole numbers or natural numbers and integers. So although number theory sounds like a really fancy thing, it's actually a fairly simple thing, and we'll be talking about this today. So factoring is breaking a number into smaller pieces, which can be multiplied to produce the number. Factorization is a key component of number theory because it talks about the relationship between numbers. So let's have a look at some examples as we factor some numbers. We'll take a look at this number, 13. If we try to factor this number, break it into smaller pieces, you can see that the only factors of the number 13 is 1 and 13. So this means that the number 13 is a prime number because it has two factors, 1 and itself, 13. Now, a different type of number is, we can see from the example, 24. If we break this number apart, we can write this as 6 and 4, 3 and 2, and 2 and 2. So the number 24 is not a prime number. It is a composite number, and it has more than two factors, 1 itself and 2 or more numbers, in this case 3, 2, 2, and 2. So now let's take a look at prime numbers. What we did just now is called prime factorization, and it's breaking a number into smaller pieces of prime numbers that are no longer factorizable. So the fundamental theorem of arithmetic states that every positive integer, excluding 1, can be represented in a unique way as the product of its primes. So let's try to take a number and factorize this number into primes by applying some divisibility rules. We'll take a look at $38,052. So we'll try to factorize this number, and we can first see it by looking at the last two digits. The last two digits, 52, it is divisible by 4. So with this divisibility rule of a multiple of 4, we can write the number 38,052 as 2 to the power of 2, which is 4, and 9,513. Now we're going to keep going down with the divisibility rules, and we can see that this number is divisible by 9. It's a multiple of 9 because if we add all of these digits together, we get a number that is divisible by 9. So we can also write this as 3 to the power of 2, 9, and 1,507. So we're going to keep going down, and we realize that we don't really have any divisibility rules for this number, but we can do simple division and find that 7 is a divisor of 1,057. And we get 151. So let's see if we can break this down. But we realize that the number 151 is a prime number. So we're going to stop here. So there we go. We have just applied the divisibility rules to factorize number. So what is the significance of prime factorization? Why are we doing it? Well, primes are very important because they are the building blocks of all integers, and there are infinitely many prime numbers. So if we simplify certain equations or numbers, we can get a better understanding of that number by breaking it down into smaller pieces. So let's take a look at an example of prime factorization. This is a 2000 Amy 1 problem. This is the first problem. Find the least positive integer n such that no matter how 10 to the power of n is expressed as the product of two positive integers, at least one of these two integers contains the digit 0. So we realize that 10 to the power of n can be broken down or factorized as 2 to the power of n and 5 to the power of n, as 10 can be factored into 2 and 5. So all we need to find is find the value of n for which either of these numbers, one of these numbers, contains the digit 0. So we're going to start with n equals 1 and go down the numbers. So n to the power of 1 is pretty obvious, 2, and n to the power 5 to the power of n is 5. We don't see any zeros in any of the digits, so we're going to move on to n to the power of 2. That is 4 and 25, and we're going to go on and on and on until we hit n equals 8, where n to the power 2 to the power of 8 is 256, and 5 to the power of 8 is there we go, 390,625, and because there's a 0 in the digits, we can say that n equals 8. All right, now we're going to look at the sieve of Eratosthenes. It's a method used to find all the prime numbers in a particular range of numbers. So this is basically similar to prime factorization, but it just helps us identify what the primes are. So the first step is to apply this is, first of all, list numbers from 2 to the maximum number in the range that we want to set the range as. And then the second step is to circle the first number not marked or circled and cross out all the numbers divisible by that first number. And number 3 is to repeat the 2 steps. So we're going to try to apply this with the number 20. So as we saw in step 1, we're going to list numbers from 2 to our maximum range, which is 20. So let's do that. 2, 3, 4. I think I have to space this better. 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so we're going to start with the first number, 2. And then we're going to cross out all the numbers divisible by 2. So we have 4, 6, 8, and so on. Once we've done that, we're going to move to the next number, which is 3. Circle that and cross out all the numbers divisible by 3. So we have 9, 12 is already crossed out, 15, and that would be it. And then we're going to move on to 5 and cross out all the numbers divisible by 5, but we realize that none of these numbers are divisible by 5. And so is 7. None of these numbers are divisible by 7, and so on and so forth. So by the time we reach 5, all the numbers would just be circled. And this is also true because we find that the square root of 20 is less than the number 5, which is the first number here. So any number bigger than 5 or equal to 5 would be circled or would be the primes. Okay, so let's take a look at some famous primes. We have the Hanna Shin primes. It's in the prime form of 2 to the power of n minus 1, where n is not divisible by all numbers greater than 1. We have the Fermat primes. It's in the prime form 2 to the power of 2 to the power of n plus 1, where n is a prime number even with and are even perfect numbers. We have twin primes, which are primes that differ by 2. Now this is Polignac's conjecture because in which this means that there are infinitely many primes with a difference of n, and the twin primes would just mean that n is equal to 2. Then we have a Gaussian prime. It's in the prime form z equals a plus bi, which is derived from the traditional primes that we know, so it would look a little bit different. And now we're going to move on to composite primes because we have just finished looking at primes. So as I have explained before, composite numbers are positive integers with more than 2 factors, 1 itself, and 2 or more prime factors. So because we've learned about the prime numbers and composite numbers, we want to categorize the number 1. And 1 is actually neither a prime nor a composite number, because if we try to factorize 1, all we get is basically 1 and itself, which is again 1. We can't really categorize this into either category, so 1 was neither of those. Now the third section we'll be looking at is modular arithmetic. So modular arithmetic is a system of integers with numbers that are reset to 0 after every fixed number n. And we use this because it helps us determine if a number is a prime number or not. And it works with the idea of remainders R. So we've probably seen modular arithmetic or modulo a lot. If we have done some coding before, we know that the percentage sign is a symbol for modulo or modular arithmetic. And it comes in the form of A is congruent with B mod n or modular n. So we'll take a look at this. In this case, we're getting B, which is a dividend, and dividing the dividend B by n, which is the divisor, and A would be the remainder. So we'll look at this by trying to find 24 divided by 7. So 24 divided by 7, this is pretty simple, right? 24 is not divisible by 7, but we know that 7 times 3 is 21. And the remainder is 3. So in this case, we would write this as 24 mod 7 is congruent to 3. Now we also realize this because if we do A minus B, or 3 minus 24, we get negative 21, which is a number that is divisible by 7, or n in this case. So as I said before, modular arithmetic is a set of numbers that resets back to the first number. And we can think of this as a clock. Modulo 12 residue, we see that instead of starting with 12, we actually start with 0. And the clock just keeps moving until we hit 12 again. So there are congruent modulos where we have more than one answer to the modular arithmetic. We find that both 1 and 5 is congruent with 9 modular 4. And we also know this because, well, 1 minus 9 is -8, and that is divisible by 4. And 5 minus 9 is divisible, is -4 and is also divisible by 4. Okay, so now we're going to move on to modulo operations. So there are several rules that we need to follow when we're looking at modular arithmetic. When a, b, c, and d are integers and m is a positive integer such that a is congruent to c modular n, b is congruent to d modular n, then we have these set of rules. So we have the addition, subtraction, multiplication, division, exponentiation rule that we need to know. But there's also one more, which is linear congruence that we will be covering today. So linear congruence comes in the form of ax plus b is congruent to c mod p. Now we'll look at an example to find x for linear congruence. So we can find x if there are two conditions, with two conditions that are held as true. First, a must be relatively prime to b, which means that if we look at the two numbers a and p, the only divisors, the biggest divisor is 1. And the second point that must be true is if b is divisible by d, the greatest common divisor is if step 1 does apply, has the solution mod p over d. So we'll take a look at this example. 4x is congruent to 2 modular 5, and we need to find x. So the first thing we can do here is actually we can do 4x minus 5x from modular 5. And we would get negative x is congruent to 2 mod 5. And the reason why we do this is because 4x is actually equal to 5x minus x, right? But because of modular 5, we're dividing anything by 5, and 5x would mean that a number is divisible by 5. This would just be 0, and we would be left with negative x. So we can write this as this form. And then we're going to divide both sides by -1 because we want to make sure that the x's are positive. So we have, because we want to be left with x, so there we go. We have x is congruent to -2 mod 5. Now at this point, what you want to do is you want to try to make this number a positive number. You don't want to keep it a negative. So what you can do is actually add this number, add this number to this number to make this number a positive number. Now, if this number was, for example, -7, even if we add 5, the number would still be a negative number, then you would just add another 5. But since that's not the case, we can just add 5 to -2 once, and we would get x is congruent to 3 mod 5. And so that would be the answer to x. That's all for today for part 1 of number theory. Thank you.